presidents of Math.lab, together with Benedetta, who is in the call. Benny, do you want to introduce briefly yourself? Okay, no. So let's go on. First of all, Math.lab is the most important student representation association here at Bocconi. So we are first of all student representatives. So we interact with the different collegial bodies in order to improve the quality of teaching in our university and university life in general. Then we also organize different initiatives in order to improve the quality of life of students, because Bocconi is studying, of course, but it's not everything. And we are by the side of the students for everything. So, for example, with the teaching division, we organize this type of labs in order to help you guys first year, mainly with the preparation of exams. So Stefano will give you some tips for the Math 1 exam, and he will solve with you so many exercises. Also next week we'll have other labs for microeconomics. So if you want to join, you're welcome. And with the teaching division, we also produce handouts in order to help you studying. So if any of you wants to help in writing handouts, you're welcome. We're happy to have your help. So now I'll give the floor to Stefano, who will start explaining Math 1, and he will give you some tips for the exam. So Stefano, you can introduce yourself. Can you hear me?
So, can you guys hear me?
Yeah, we can hear you.
Okay, perfect. So, hi everyone. My name is Stefano Graziosi, and I'm a second year BM student here in Bocconi. Last year, I was literally in your shoes, probably complaining about Math 1 and all of the proofs and everything we had to do. But yeah, I mean, those labs saved my ass last time, so I thought it was nice to give something back and do it again. And here we are apparently. So before we start, we're just going to go through a basic mock exam, the one provided by Bocconi, and we're going to reason through the questions, the answers, and clear any doubts you guys may have. And before we start, do you have any questions? Anything you'd like to know about the exam, the structure of the exam, or how the grading works? Please feel free to either turn on the mic or just write in the chat. Thank you.
Guys, can you see Stefano? Because Stefano, I don't see you.
Oh, that's a shame. I have my camera on, but apparently the Wi-Fi is not as good as I expected it.
Okay, you can start, trying to share the slides, or if you have something. So maybe they
Yeah,
work.
sure. Just a second.
Okay, we can see the screen. That's the important part.
Okay, so hold on a second. Let me quickly cancel those things. And here we are. Can you guys see the screen or? Okay,
Yes,
shall be clear now. So before we start, any questions? Oh, I can see something in the chat. Nope. All right. Seems everything is pretty clear. So, hello. I was wondering the list of proofs. Winifred is partial. I heard it. Yeah, it's indeed different from last year. We went from 32 proofs last year to I think around 39 or 40. You can find all of the information in the syllabus. You just need to go on the Blackboard, courses, 362 math, and you'll find everything listed on the syllabus. It's quite long. It's not very convenient to find everything, but I'm afraid that's the only option. An actual list is not provided as of right now. Hope it's helpful. Okay, great. So did you guys already have a look at the exam? Do you know how it's structured, how it works? A few people answering is enough. Oh, yep. Thanks, Angelos. Very appreciated. So I think you can start with the first question. consider f going from R to R, strictly increasing. Then, well, in this case, we have four options. The first one, f is unbounded. The second one, f is quasi-concave. Third, f has bounded lower contour sets. And D, none of the preceding. Well, the first thing we can do is think about the information we're given. In this case, we know just one thing, that the function, aside from going to R, is strictly increasing. We really care about this because we know that monotonic functions, just like strictly increasing functions, on an interval are always quasi-affine. Do you guys remember what affine means? Because I think we can start writing. Okay, more and more people are joining. Just a second. Here we are. So, where is it? Let's start by giving the definition of affine function. An affine function is a function which is both concave and convex. Sorry, just a second. Okay, connection is not helping us today, unfortunately. Here it is. But then once we can say that the function is both concave and convex, in this case, the function is increasing, not monotonic. Therefore, we can say it's concave. But then what else do we know? Whenever a function is concave, then we can also state with certainty that it's quasi-concave. Therefore, it's safe to say that the correct choice is choice B. Oh, wait, let me actually say B. And here we go. So that's it for question one. Moving on to question two. Consider two sequences, AN and BN, such that AN times BN converges to 4 as n goes to infinity. Then we have four options, just like the previous time. So in this case, what we need to think is, are they both convergent? Are they both bounded? Are they both monotonic? Well, first of all, we'll start by stating the obvious. So do you guys think we need both of the series to be monotonic? Well, chances are we don't. It's really too much. We don't need it in this case. So I think we can already cross the monotonic. And then we have the slightly trickier part, we can call it. They are asking if the series are both convergent or both bounded. But let's recap. One thing I didn't know at the time was, or at least I didn't know very well, difference between, in this case, convergent and a bounded series. So let's say a sequence is convergent if there exist two numbers such that all the if the value of the terms tends to a fixed number as the number of terms keeps on increasing. Instead, a sequence is bounded if there exist two numbers such that all the terms of the sequence lie in between those two numbers. Let's give an example. Consider the sequence, well, let me erase this, 1 over n, where n is, of course, a natural number. So n belongs to n. As n goes to infinity, let's write it, n goes to infinity. The terms of the sequence tend to 0. Why is this? Because we have 1 over 1, which is of course equal to 1, 1 over 2, which is of course equal to 0.5, 1 over 3, which is etc., etc. So what we find out is that as n goes to infinity, as we said right here, the whole series goes to, 0, actually. The whole sequence goes to 0. Further, we can also state that the biggest term we have here is 1, which we will call our maximum. Oh, but we can also call it upper bound, can't we? No. And another thing we can see is that, of course, going on further and further, we have 1 over infinity, which is, let me rewrite it, 1 over infinity, which is, of course, equal to 0. We can get 0 and call it the minimum. Hence, any number greater than 1 can be considered an upper bound, and any number lesser than 0 can be considered a lower bound. Therefore, this sequence is also bounded. So we know that 1 over n is both, we can say, both convergent and bounded. At this point, let's consider another sequence, which is sinus of n, which with n, of course, being a natural number, just like before. No term in this sequence is lesser than or equal to -1 or greater than equal than 1. So what we're saying is that once we take our graph, of course, this is a sketch, so it's not going to be exactly precise. We're only going to take values for, let's say, 1, 2, well, let me do it more precisely, 1, 2, 3, 4, etc. Well, we see that the top value here is 1, and the lower value here is -1. So we can say that this sequence is bounded, correct? But at the same time, we know that as n goes to infinity, this sequence never converges. Therefore, we can say that it is, let me get some different colors. It's bounded, but not convergent. Keep in mind those examples, guys, because sometimes you may also be asked during the exam to give an example instead of an answer. And this is very useful in case you will meet this scenario. It personally happened to me, so yeah, just keep an eye open for that. At this point, going back to our main questions, we can say that we don't really need both of the sequences being convergent or both of the sequences being bounded at the same time. So we can exclude both of those. The rationale behind this is that, yeah, we do need them to converge to a certain point, but we do not need both of them to be either both bounded or both convergent. And this only leaves us with option D, which is the correct choice. At this point, question 3, which I really liked because it's really easy. I mean, it's easy once you know the rationale behind it, of course. We have the sequence an equals n to the power of 3 over k to the power of n. In this case, we just need to use a principle called, you may have studied it, well, you will probably, hierarchy of infinities. What does it mean? Is that, of course, we have various infinities and some of them are stronger than others. For example, the limit of as x goes to infinity of logarithm of x is lower infinity than, let's say, same limit. X goes to plus infinity, of course. Oh no, I was supposed to click on paste. And here it is, of, let's say, e to the power of x. So this one is smaller infinity, and this one is an infinity of higher grade. So we can call it bigger infinity. Those terms are not precise. The precise terms are infinity of lower order and infinity of higher order. So lower order and higher order. And here we are. So going back to the question, what do we need to do? We need to make sure that, of course, this sequence converges to 0. Well, converges actually. So we need to make sure that the degree of the denominator as n goes to infinity is greater than the numerator. How do we do this? We can also study the examples that we have. So in case k is greater than 0, and the denominator may also be, let's say, 0.9. 0.9 to the power of 2 is equal to 0.81, which is a lower number. This is not what we're looking for. At this point, we also have k greater or equal to 1. Let's take the limit case, which is k equal to 1. If k is equal to 1, we have 1 to the power of n, and the 1 to the power of n is always 1, as we all know. Therefore, this also doesn't respect the condition that we need to have. At this point, we have k greater than 1. Let's see. We have that 1.01 to the power of 2 is going to be greater than 1.009 to the power of 2. This is exactly what we're looking for, something that as the exponent 2 goes on, it's greater and greater. So wait, let me actually redo the example. 101 to the power of 3 is greater than 101 to the power of 2. All right, this is the correct one. So in this case, we can see that yes, C is what we're looking for. And of course, every value of k is wrong for a simple reason. It also allows for negative numbers, and it allows for numbers between 0 and 1, which we know are not what we're looking for. Therefore, we can clearly state that the answer we're looking for is C. At this point, we move on to a more theoretical question. Consider the two series, well, let's just call it AN, this one, and BN, the other one. We're given 4 options. The first one, if AN, BN tend to the same value, L belonging to R, the two series have the same behavior. Then we have, if the two series are convergent, then AN and BN tend to the same value. If the two series are divergent, then A and B tend to the same value, none of the preceding. Well, just judging by common sense, I think we can say that option C is wrong. Of course, if the series are divergent, then they cannot tend to take the same value. Does it make sense to you guys? But we'll take it as a yes. So moving on, at this point, some of you, the ones who have already studied a little bit, may have realized that we need to use a theorem, the necessary condition for convergence for a series indeed. So let's go quickly over it. We said this is question number 5, so let me write it here. Necessary condition of convergence for a series. What do we know? By definition of the proof, we know that if a series, let's say, like this one, AN with n equal to 0, converges and has a sum equal to S, then AN will tend to 0. And we also have the proof. So let's get quickly over the proof. Of course, you will not need to demonstrate it, but you may be asked the theorem itself. Therefore, it's always useful to remember the rationale behind everything we do. Even though we not need to show it, it's good also to double check on what may be the errors we are doing or the errors we are avoiding indeed. So we have that by hypothesis, the limit for n which goes to plus infinity of Sn is equal to S. At this point, we need to recall that An is equal to, wait, let me distance it a little bit. An is equal to Sn minus Sn minus 1. This element right here is just the previous element from this thing. So nothing too complicated. It just means, in simpler terms, that Sn is equal to Sn minus 1 plus An. I find this version right here a little easier to remember, but that's just me. It's all a matter of, you know, personal preferences. Let me get some real estate. And at this point, let's move on. It is sufficient to apply the limit at this point. Oh, well, we need to take another consideration. Of course, we stated that this part, the limit, the sum is S, but we also need to consider that the limit for n going to plus infinity of Sn, well, Sn minus 1 equals to S. At this point, we have three elements, which we will call number 1, number 2, and number 3, of course. We can just take the limit of the first equation that we had, which, well, in our case, is the third. We can take this equation and substitute what we found. So substitute with the limits. The limit of a n as n goes to positive infinity equals the limit, of course, n going to positive infinity of Sn minus the limit of n going to positive infinity for Sn minus 1. At this point, we can substitute. So keep in mind this formula. For the sake of clarity, I will just copy and paste it. Let me actually create our page. Okay. So, of course, we have that this part here is equal to what? S. And this part here is equal to, well, unsurprisingly, S. So we have that this limit, let's copy and paste it. Where's the zoom again? Here we are. Is equal to S minus S, which is equal to 0. We have just demonstrated the convergence, the necessary condition of convergence for a series. That being stated, we can now focus on the question. Here we are. So if the two series are convergent, then an and bn will tend to the same value. Thanks to the theorem we just employed, we can safely state that if both our series in yellow and the series in green converge, just like it says here, if the two series are convergent, then an and bn will tend to the same value. And this is indeed correct. So the question, the answer instead is B. Okay, moving on to number 5. This series, and well, we can see a series right here. We will again color it in yellow, converges if and only if. At this point, the first thing that we should do, does anybody have the mic open by any chance? David? Oh, cheers, mate. Okay, moving on. We were saying this series converges if and only if A is lesser or equal to 4, A is lesser than 3, A is lesser than 4, and for every value of A belonging to R. First, we need to do something. We need to see the terms we have here, and the terms are, of course, 2 to the power of minus n to the power of A, n to the power of 4 in the denominator, and square root of n in the denominator. Of course, we can also rewrite those terms, but we're not going to need it. What we need to do in this case is just to focus on the most important factors. And what are they? Of course, they are the factors with you know, the higher number as they go, the greater degree of infinity, the greater hierarchy of infinity as they go to infinity, as we were saying. So those terms are n to the power of A and n to the power of 4. At this point, we realize that we can use the comparison criterion, which is one of the three criterion you're going to need to use to study the behavior of series. And do we see any resemblance to any known series? Well, perhaps we do, because this actually looks a lot like 1 to the power of n to the power 1 over n to the power of alpha. And what else do we know? We know that if alpha belonging to natural numbers and alpha being greater than 1, we know that this series converges. So let me write it.
Stefan, I think you have a question.
Oh, thank you. Oh, thank you. How do we know when we have to use the comparison criterion or the ratio criterion? Well, I know this answer is not what you're looking for, but most of the time it comes down to exercise. So I personally use the convergence criterion whenever I see something that looks like a series I've seen before. You'll find plenty of series with, n to the power, with n to the power of alpha over n to the power of 4, or vice versa. You may have n to the power of 5 over n to the power of alpha. It happens very often in the exams. So whenever you see a situation where you feel like you need to take out some options in the equation, I just use the convergence criterion. And for other circumstances, of course, I go with the ratio criterion. If you want, we can talk a little bit about this thing at the end of the recap, but please remember me about this thing. But yeah, short answer, I say it's a matter of experience and exercise. So over the next few days, perhaps try to look at some examples and try to familiarize yourself with how it works. So moving on, well, actually, getting back to question number 5. We have that 1 over n to the power of a converges if and only if a is greater than 1. So let's see. In our case, I think we're going to need to have another page. This was actually number 4. I just noticed. All right, better late than never. And here we have number 5. So let's go to number 5. We only need to take into account the series of n to the power of alpha over n to the power of 4. And notice the similarities with the series of, well, actually, 1 to the power 1 over n to the power of at least 2, let's say. At this point, we know that we have a few options, either alpha less than 4, alpha less or equal to 3, and alpha lesser than 3. Do I recall correctly? Oh, no. Well, less or equal to 4. Apologies. Less or equal to 4. Less than, wait. Less than 3 and less than 4. At this point, it's just a matter of trial and error. So let's say that we plug in less or equal to 4 in the first part. What do we have? The higher number we can get is, of course, 4. So we say 4. And we just find ourselves with 1 over 1. We know that the series of 1 over 1 is just series of 1, which eventually goes to infinity. At this point, what else do we have? We found out it's not this option. We can cross it. Then we have alpha lesser than 4, smaller than 4. So let's plug in, well, the highest number we can get, which is 3. And we find ourselves with 1 over n. Of course, series of 1 over n. We know this is also not the scenario, because we're still looking for this thing. At this point, I know you guys have seen it. The only option left is, of course, alpha lesser than 3. Of the first number we have, the first natural number we have, this is very important, is n to the power of 2 over n to the power of 4, which is equal to series of 1 over n over 2. And as we've all seen, this equation is, this series is actually exactly equal to what we were looking for. Hence, we know that the answer to this thing, crossing out this option, and of course also this one, which should have been clear from the first moment, but it's not the option, we are left with B. At this point, let's move on to question number 6. If f is defined in A being a set which goes from -1 to 1, excluding the extremes, and the limit of f goes to 0, of f of x for x going to 0 is equal to 0, then what can we say? I think it's useful to take an example. In this case, we said we're doing question number 6. Let's go through the options we have. So, hold on a second. Here it is. There exists a neighborhood where f is bounded. So the important thing is that f is bounded. A neighborhood where f changes its sign. A neighborhood where f is continuous at x0, and none of the preceding. So I think the first thing we can focus on is answer C, because in this case, we truly have nothing suggesting us that the function is changing the sign. There is literally nothing worth mentioning about changing the sign. It's just defined in A and limits going off 0. So I think it's safe to say that it's not option C. At this point, I think that's a little tricky and maybe, a little problem. F is continuous at 0, x equals to 0. This is not the case, and we'll see why. We know that the definition of limit is that, of course, limit of x0 equal approaching 0 of f of x is equal to x0 approaching 0 from the right of f of x, which is equal to limit of f of x for x0 approaching to 0 from the left. So what does it mean? It means that if we have a function like this one, just a second, it may be the case that we have a discontinuity right here when the point x equal to 0 corresponds to y equal to 2. Of course, the limit of this specific point, if we calculate the limit for x approaching 0 of f of x, well, let's actually call it x to the power of 3. Well, apologies, f of x. It's not x to the power of 3 because we have this little tidy element. Of course, this limit is equal to 0. But then we know that f of x, f of 0, is equal to 2. So no, we can state that this function, the function that we just described, this one, respects everything that was in question 6, but still is not continuous at x equals 0. So we can also cross this option. What we're left is either it is bounded or none of the preceding. Now, knowing that we are excluding the limits, so -1 and 1, let's do another little example. Okay. We know that those points, okay, just a second, I'm having a few notifications. Oh no, it's just people joining, I'm sorry. So limits are not included. And at this point, we have defined in A going from -1 to 1, and we know there's no asymptote in 0. Therefore, when we have you see, a function which is defined in a closed interval and without asymptotes, then we can also state that there must exist a neighborhood, even if it's very small, but there must exist a neighborhood where this function f of x is bounded. And this is by definition of just knowing the, of course, the dominion and the fact that there are no further asymptotes in the middle of our graph. So after excluding by logic and common sense option C and option B, we can state it's actually A. So moving on to question 7. Question 7 is just a matter of, computations. So I'm solving it, yeah, but chances are that photomath can do the exact same thing. So in case you find yourself worried or you don't know how to solve some of these problems because they might appear challenging, especially if you haven't studied limits in high school, which is the case for quite a few people, I know. What we're going to do to, cut short is just to take this limit and apply the L'Hopital theorem, which just states that the limit of this thing is exactly equal to the limit of the derivative of the denominator over the derivative of the denominator. By calculating the derivatives, we have that d over dx of everything. I'm just going to write it again. We can now calculate it. So the bottom one should be clear. It's 2x plus 1. And the top one should be e to the power of sin x plus cos x. Now, let me double check for just a second.
Stefano, I think you have a question or something in the chat.
Okay, we haven't done L'Hopital. We solved it asymptotic equivalences. Oh, thank you so much. Okay, I was already going a little too, well, I was not following the program. So in this case, I'm not going to lie. I think I'll have to review asymptotic equivalences, as I can assure you guys, you're not going to use them any longer in your life. If you ever find a problem like this, and chances are really slim, you're going to solve it with L'Hopital. But in the meanwhile, yeah, I think if it's okay with you guys, I think we can go over this question at the end of the session, just not to waste time. We'll put a little exclamation point close to it, so we know. At this point, we have question number 8. Let f belong from A belonging to R be a continuous function. Then f certainly has a minimum if, well, in this case, whenever we have a function like this one, oh, let me get number 1. Here it is. A function like this one, which is continuous, and we are asked for a minimum or a maximum, we know that we need to use Weierstrass theorem. It's very easy. So it's part of the 3 or 4 theorems you guys need to know. They are at the end of the program. And whenever we need to apply a theorem, what we need to look for is for the validation of the hypothesis. So what are the hypotheses? Let me go back to the theory for a second. And here it is. A, our set, shall be closed and bounded. When we have a set which is closed and bounded, it's also compact. So we just need to see whether any of our sets, so A equals R, A equals N, A equals, well, 1 to 2, and A equals this other set 0 to 3 union with 10, we need to find which one of those is compact. Of course, if you recall the definition of compact, you already know that we can eliminate option A, we can eliminate option C, and we can also eliminate option B, as we have this tiny sign which says that 2 is not included. Therefore, it's not closed, and hence it cannot be compact. At this point, we are left with a single option, which is D. And indeed, if we verify the hypothesis, we have 0 to 3, which is closed and bounded, and 10, with, of course, being a single point, is also closed and bounded. Therefore, it's safe to say that the correct answer is D. And here we are. So is everything clear about this sheet? Is there any question you'd like to go over, apart from question 7, of course? Oh gosh, yeah. Thanks, Bartu. That's very, oh my gosh, such a silly mistake. I think I already canceled it, but yeah, it's actually multiplied by cos x. It was my mistake. Thank you for noticing. So one small thing, guys, I should have mentioned it earlier. For these types of questions, of course, the professors are not going to evaluate the methodology that you use. So, of course, you can use asymptotic equivalences, but if you're also confident with limits and derivatives, I kind of suggest using L'Hopital, also because you're going to use a piece of paper which the professors are not going to grade. You're just going to either keep it for yourself and destroy it, or just throw it in the trash. So I think we can still go over our question 7 really quickly. So we were saying derivative of e to the power of sin x minus 1 over derivative of d to the power of dx x squared plus x. This point, e to the power of sin x cos x 2x plus 1. And now we need, of course, to take into account this tiny thing, which is the limit. As x goes to 0, we know that all of these goes to, well, actually, let's say sin of x goes to 0, cos of x goes to 1, and of course, e to the power of 0 goes to 1. So we find ourselves with e to the power of 0 times 1 over 2 times 0 plus 1. Of course, we have 1 times 1 over 1, which is 1. So we have not used the proper method, perhaps, but it's a little quicker and it's going to help you if you're running short of time. Keep in mind that the math exam is supposed not to be finished, so if you can manage to save some time by using some method you're more familiar with, I strongly suggest using this method. But still, if you want to use the correct one, that one is the asymptotic equivalence method, as Valentina Benedetta was saying before. Could you repeat why A is correct for question 6, please? So, okay, let's go to our paper sheet. Suppose that we have, I don't know, any function which may look like this, may look like, I don't know, also this, may look like this. So the important thing is that, of course, where is it? Defined it -1 to 1. The limit of f as x tends to 0 is 0. We need to find a neighborhood where it is bounded. A neighborhood, wait, let me actually do those things a little nicer. Okay, so this is 1. This is another one. And this is the last one. We can always find a neighborhood. Maybe this neighborhood may be from 1 to 1, -1 to -1 to 1, my bad, such as the case of the function in f. So we know that this function has, well, actually, this function has no minimum or maximum. It's always constant. Let's focus on the second example, which we'll call f of x. Let's take a sample neighborhood. Let's say that is -1/2 and 1/2. And we know that it has a minimum here and a maximum here. But also, we may have so many different examples. We may have a function which looks like this. We may have a function which is, I don't know. I think we're going to need another one of those Cartesian planes. Suppose that now, for the sake of clarity, we're going to put -1 here and 1 here. And suppose that we have a function like this, which is actually a transformation of the function y equals sin of x. Right. So at this point, we know that this function, we can clearly find a neighborhood where we have a maximum and a minimum. The maximum is going to be here. The minimum is going to be here. Okay. In this case, we can find a neighborhood where it is bounded. There exists a neighborhood where it is bounded. Once we have stated this, we can also affirm with certainty that there exists a neighborhood U. Oh, a neighborhood U of 0, so U of the origin, where this is bounded. In this case, we're just going to need to do, well, this tiny thing. Okay, now it makes a lot more sense because the maximum is here and the minimum is here. And it is crucial, of course, that's the little step I have not mentioned. The neighborhood of 0, and this directly relates to the fact that the limit of f of x for x tending to 0 is 0. So that is the crucial thing. We have the certainty that there exists a neighborhood where it's bounded, but there's no certainty that there exists a neighborhood where it changes its sign. So the first thing, going back, the first thing we should have done was to say, okay, we know this part. We know this part. Now we should only focus on whether it's option A or C. And once we say that there's no obvious thing suggesting us that the function changes sign, it should be pretty clear that the only other option left is that it's bounded. So if we go by logic, if we go by common sense, the first two options we exclude are C and B. Instead, if we go by mathematical definitions, the first thing we notice is that we should actually eliminate option B and D. Let me use the color purple so it's a little more different. So I have mentioned another little thing, the difference between a purely mathematical approach and a more common sense approach. My personal advice, if you're struggling with time, is to go for a, well, let's call it common sense approach. Why? Because more or less, we all tend to have common sense. We all tend to realize the same things. Instead, when we go for the mathematical approach, we need to be very confident in our skills and in what we know. So I strongly suggest going for the purely mathematical approach if you know you've studied everything. Otherwise, for these types of questions, you can just think about it for a second, say, okay, this is sound, this is not sound. So I'm doing this and I am not doing that. And I think that's pretty much it. At this point, we also have, of course, the open-ended questions. So if you guys want me to go over any of those questions, otherwise they are really well explained in the notes, in the solutions. For proofs, are we supposed to follow the teacher's method or the textbook we were given? Because both lead to the same conclusion, however, the proof method is different. So at the end of the day, every method is fine, because for math, instead of other exams, both the methods suggested by the professor and the methods suggested by the book lead to the same exact outcome, as you said. So just pick the one you like the most and stick with it. The only suggestion I have is that once you stick with, you see, let's say you stick with your professor's method, then always go with it. Otherwise, if you prefer the book method, just stick to the book. There's no preferred proof. It's just a matter of getting to the conclusion. Do you guys have any other questions, any doubts, anything you'd like to go over? Okay, if we don't, then I think we can just briefly mention how grading works. So I know some of you are worried. Oh, the regularity theorem. Okay, for series. Let me look through my notes. I'm sorry for the dead times, but it's a little complicated. Okay, this is for link. Okay, I'm sorry to disappoint you, but I am afraid the regularity theorem is among one of the 7 or 8 theorems that were added this year. I cannot find it in my notes, so if you have any screenshot, perhaps we can elaborate on that. I will quickly type my number in the chat. So feel free to send me a text and I'll just share it on the screen. Regularity theorem for series. Sure thing, no hurry. In the meanwhile, I'll just briefly talk about the grades. So seriously, do not worry about your performance in the exam, because wait, let me turn on my camera actually. I think we're not going to need the screen sharing. So it's fairly easy, it's fairly straightforward. Last year I think it was 53%, which roughly corresponds to 15, 16 out of 30, but the curve really helps you a lot. For example, last year, people were given from 11 to 14 extra points just for the first partial. So if you're like, oh, I think I got half of the questions wrong, well, in this case, congratulations, because chances are your score is in between 26 and 28. And this is just to say, probably it's one of the toughest exams of the whole 3 years, probably. But that's just on an absolute level. In reality, thanks to Gauss, you're going to have great marks. And I can tell you by experience that whoever shows up and attends even those tiny recap sessions ends up having a tiny advantage over the rest of the guys. So wait, we actually have a question. So were the theories proofs were added or omitted? So last year we had 32 proofs and this year you guys have 39 or 40 proofs. I cannot remember the exact number. So they actually removed a few of our proofs. I have them on here. Wait. They removed a few tough ones, but instead they added quite a lot of, slightly easier ones. So for references, for all of the proofs, you can find the material in the Blackboard folder called syllabus. Okay. So we now have the proof. Regularity theorem for series. Just a second, I will share the screen in a moment. Okay, proof. Since an is greater than 0, at least every n must be greater than. Okay, let me actually get my tools, and here we are. So what do we know? Oh, hold on a second. I think we might have done it just under a different names. We didn't have a name last year. Okay, so for any series eventually greater than 0, we have that n is always greater than n with this little sign. And at this point, if you guys recall, this formula is exactly the same one we saw here. So I think we can quickly import the file here, and voila. I think, yeah, this is an A, and eventually greater than 0. Then we have S and equal S and minus 1. Oh, wait. Can you send the notes that you took during this session? Yeah, of course. If you guys can just leave your email, I think that's the easiest way to share the notes. Of course, if you want them. If you don't send your email, we're not going to look for you. So let's go back to the proof. Valentina, feel free to text on the chat so everybody can see the questions. Or if you want to speak up, it's the same thing. So the doubt is on the bounded conditions. And yeah, Valentin is asking me, does the series need to be bounded in order to be convergent? And well, I think we can just go over what we said a few slides ago. Basically, every sequence which is bounded, every sequence which is convergent is bounded, but not all sequences which are bounded are also convergent. So in this case, it does not necessarily need to be bounded in order to be convergent, Valentina. I cannot see the chat. Oh, here it is. The bounded condition. At the end of the day, no, it does not necessarily need to be bounded. If you want, I have some notes from last year. Let me see if I can find them. Yeah, here they are. So no, let me briefly say. we can write a little note here. A convergent series is necessarily bounded, always bounded. A bounded series is not always convergent. Okay, so I think that's it. If you guys have any more questions, anything you'd like to discuss, I mean, I'm here, so yeah, feel free to speak up.
Okay, Stefano.
No worries.
Stefano,
See?
have you finished, or do you miss something?
Okay,
you're done.
I think we're done. Like, if nobody else has any other questions, I think we can just do it.
Okay, perfect. Then, guys, you can contact Stefano like whenever you want. You can leave your email or something, so or your number, so everyone can send you messages.
Sure thing. I mean, my number is somewhere up in the chat. Feel free to screenshot it, or I'll just write it again. Of course, the prefix is the Italian one, plus 39, in case you don't have an Italian phone number, but yeah. We will, can you do theorem 1 for 6 in the other case? I'm afraid I don't have the numbers for the theorems. That might be a recent introduction, because last year's we just had names like these ones, like De Morgan, without proper numbers. Should be a set is closed if and only if its complement is open. Well, it's funny because I have to go for the notes, which are 1 year old. Yeah, indeed, there's a theorem for this. A set is closed if and only if its complement set is open. If you want, I can send you the picture, or I can just write it on the iPad and then send you the file. We only have the inverse assembly book. Feel free to leave your email, or if you've left it somewhere above. Yeah, if you could just write it again, that would be great. Sorry. And aside from this, I think we're done. So it's been a pleasure, guys. Hope I've been helpful. If you have any doubts, anything, feel free to reach out to me. You have my number, and chances are you also have my email. I mean, you don't know if you need it, but well, Stefano.Graziosi. It's the usual Bocconi ones. And that's it. I hope to see you again for the microeconomics lab, which I think we can already say is going to be held next week. And I think that's it. So if you find it useful, oh, someone just joined. Weird timing, but all right. And yeah, that's it. So I'm going to be here for 5 to 10 minutes, as long as we need to. But just in case, if you need anything, hit me up. Always here.